Hi, and welcome to this review of the radical substitution mechanism for alkanes. This clip should be viewed after you've done your independent study and notes, and they need to be in front of you ideally to support the work you've done, because that's what this clip is designed to do. So first let's have a look at what a radical actually is. It's an uncharged and very reactive species with an unpaired electron. So the little dot by the symbol is the unpaired electron in each case, but unfortunately this gives the radicals extreme reactivity and makes them environmentally problematic in many cases, which we'll look at now. So as you can see, all of them in some way or another are involved in either damage to the atmosphere or environmental threat to ourselves. And for this reason it's important to have an awareness of how these particular types of species react. So why don't you pause the clip and see if you can write out the dot-cross diagram for the methyl radical, which is CH3 dot. So you need to think carefully about which atom could have an unpaired electron in this radical. So hopefully you came up with something like this. The carbon atom carries the unpaired electron, but it has to use the other three to form three covalent bonds to hydrogen atoms. Remembering obviously that carbon has 4 electrons in its outer shell. So let's now have a look at how radicals are formed in the first place. To do this we need to introduce another term called homolytic fission. It's a type of covalent bond breaking where one electron from the shared pair goes to each atom. So the thing to do now is to copy this out and see if you can complete the dot-cross diagrams according just to the definition of homolytic fission. So one electron from the shared pair goes to each atom, so the covalent bond is broken. So hopefully you also came up with this idea. So each of the electrons in the covalent bond went back to the atom that it came from. Now this process obviously requires energy, and usually this is supplied in the form of UV light, although strong heat can do the same job. So there's a specific way you write this in equations. There's actually 2 possible ways you could write this. You could write it as Cl2 going to 2Cl dot, or you can do it as Cl2 going to Cl dot plus Cl dot. This is in fact the first stage of the chlorination of an alkane. It is called the initiation stage. So what we're going to do is take you through the different stages, one by one, of the radical substitution mechanism for chlorination of methane. So what happens next is the chlorine radicals can attack a methane molecule. So the next stage is called propagation. So what happens here is a radical attacks a molecule to make a new radical, in this case CH3 dot, or methyl radical that we talked about a bit earlier, and HCl. So propagation is actually defined as a radical attacking a reactant molecule to create another new radical and another molecule. Now it's important to remember that there's many possibilities, but usually, unless they specifically ask for all the possible propagation steps, 2 propagation steps will be enough to get the marks in an exam answer. So one of the possible combinations is shown in dot-cross diagram form there, but there are others as well. If you think carefully about the different radicals that are available, as well as getting 2 different radicals reacting with each other, like I've done in the dot-cross diagram, you could also get 2 of the same radical reacting with each other, such as 2 Cl's radicals making Cl2 again, or 2 CH3 radicals making ethane C2H6. So like I said, there's a number of possible combinations, and I've also mentioned the many possibilities you have with propagation as well. I want to take a little bit more time to go into that now. So depending on the amount of chlorine molecules that are present at the start at initiation, if there are lots of them, the new radicals made in propagation steps can react with these chlorine molecules. And what happens essentially is that chlorine is substituted for hydrogen on methane repeatedly over and over again to get multiple substituted methane molecules. So in this case there's excess chlorine at the beginning. So what happens is that there's many Cl radicals available. So basically what happens through a series of propagations is you gradually replace all of the replace all the hydrogens with chlorines. So you end up with the bottom equation, which is the finishing one. So you get CCl4 plus HCl. At that point, it doesn't go any further. So as a result, it's quite hard to control the products. So it's actually not a very good method for making haloalkanes, because the radicals are so reactive, once they actually start reacting, it's almost impossible to stop them. Okay, so hopefully this has proven reasonably useful in taking through the basics of the three-stage process: initiation, propagation and termination, and explored whereabouts to place your dots, and also to make sure you're happy with how further substitutions during propagation, depending on whether it's excess Cl2, for example, or excess CH4, you can actually control what sort of products you end up getting. Now, when I say control what sort of products you end up getting, what I mean is what sort of substitutions do you get? Do you get substitutions by chlorine radicals, or if you have excess methane, do you get substitution by methyl radicals? Either way, if you want a specific haloalkane, so for example, it's almost impossible to stop the reaction at dichloromethane. So the same would be true for CH3Cl or CHCl3 or indeed CCl4. Okay, so that takes us to the end of this clip. Hopefully it's covered the three stages and also explored possibly what happens during further substitutions during propagation. So as always, thanks for listening, and until next time, see you soon.